Hello, today I'm going to discuss scientific data file formats. Last time we talked about the concept of scientific data models. Now it's time for us to look at a few common scientific file formats and see how they are related to the concept of data models. The file formats that I'm going to cover in the following include VTK, NetCDF, and plus3D. In this video, I will only focus on VTK. Conceptually, those different file formats have very similar data models, although they have slightly different way to store the domain structures, the attributes, and metadata. Also, different file formats have different complexity, which means they have different extensibility to store one, multiple, or groups of data objects. Furthermore, some of them are not just file formats, they are actually software library with APIs that allow people to read, write, and query the data. The first file format I want to discuss is the VTK file format. This is the file format used by the popular software visualization toolkit, which is an open source, free available software made by the company called Kitware. VTK implements a large number of visualization algorithms. It can process many different types of data and has been used by many scientists and visualization researchers. VTK file format contains two different styles, a simple legacy format that has been used from the beginning of the software, and also a more modern XML-based format. In this lecture, I will talk about the legacy file format so that you don't have to worry about the syntax of XML. A legacy VTK file format contains five main parts. The first is the file version number and identifier. This is a simple line of text starting with a pound sign. Then we have a header, which contains any information that you want to put about the dataset. The header can have up to 256 characters, ends with an end of line symbol. Next, we have the type of the file, which is either ASCII or binary. So far, what we have seen is just simple information about the dataset. After those, we can begin to write the actual data. Like we discussed before, to describe a scientific dataset, we need to specify the domain structures, i.e. the mesh, and the data attributes. Now let's look at the details how VTK specifies the structure of the domain. Remember, the domain structure is to describe the positions of the sample points and how the points are connected together. That is the mesh. To specify the domain structure, we first begin the line with a keyword dataset, followed by a particular type of mesh that connects a sample point in the dataset. The options are structured points, structured grid, unstructured grid, rectilinear grid, party data, and field. After that, we will need to provide the information specific to the type of the grid in use. The typical information that needs to be provided includes dimensions, grid spacing, coordinates of the sample points, etc. For structured points, we need to specify the dimensions in XYZ, that is, how many points along X and Y and Z directions, the position of the origin, and also the spacing between the adjacent points in X, Y, and Z direction. With the information, the position of the point can be inferred easily if we know their IJK index. Note that for structured points, there is no mesh and the points are not connected together at all to form cells. For rectilinear grid, we need to specify the dimensions in X, Y, and Z. That is, how many cells you have along X and Y and Z directions. And also, since for rectilinear grid, the spacing between the adjacent X, Y, and Z grid lines can be different. We need to specify the position of the X grid line, the positions of the Y grid line, and also the position of the Z grid line. For unstructured grid data, because there's no regularity in the positions of the sample points, we need to specify, first of all, the number of points that are in the mesh, the data type used to specify the positions of the points. The type can be what you see in the box. Then we have to specify the positions of each point, and then how the points are connected together to form cells. To do this, we need to specify, first of all, how many cells are in the dataset, what is the total number of integers used to specify the cell list. And then for each cell, you need to specify how many points are in each cell, the position of those cell corners. Those can be specified the integers pointing to the earlier point array we just seen. In VTK, it is also possible for you to mix and match cells of different types. For this reason, you need to specify the types of VTK cell for each of the cells. Here is a list of cell types that are supported by VTK. In VTK, you will specify each type by an integer number. For example, 1 represents vertex, 2 represents polygon vertices, 3 represents line, and 4 represents polyline, and so on. You can also have 3D cell types. They include tetrahedron, voxels, hexahedron, wedge, and pyramid. Now let's move on to talk about the final portion of VTK file, the data attributes. To specify attributes, first of all, we need to specify the type of the attributes. The data attribute that VTK supports include scalar, vectors, 3x3 tensors, surface normals, texture coordinates, and something called field attribute. After that, we need to provide a name for each attribute. This name will allow the user to retrieve a specific attribute later that they want to visualize through the VTK APIs. After the data name, we need to provide the type of the attribute. Finally, the actual attribute values should need to be provided. As an example, let's see how to define scalar values as the attributes. So we first have the keyword scalar, followed by the name of your choice for the data, the type of the scalars. Remember, it can be integer, floating point, etc. And also the number of components in the scalar attribute. VTK allows 1 to 4 components for the scalar attribute, and the default value is 1. VTK also allows you to specify a color lookup table to go with the scalar attribute, which will allow one to map the scalars to colors when generating visualization. This lookup table is optional. If you do not have your own color table, just write default. After the necessary header information and scalar values of the specified type should follow. For vector attributes, we first start with the keyword vectors, followed by the name of data as usual, and then the type of the vector values. Then you need to specify n 3D vectors. Here, n is the number of grid points. One thing you'll notice is that VTK assumes your vectors are always 3D vectors. Defining tensor attributes is very similar, except that you are going to supply n 3x3 matrices as the tensor, where n again is the number of grid points you specified earlier in the domain structure. This slide shows you how to define surface normals and the texture coordinates as the attributes. As you can see, they are very similar to how you define vector attributes, except that you need to specify the dimensionality of your texture coordinates.